Let's wait for a few more seconds before it starts. Okay, now it's 2022. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to EE21. So today's lecture will be the 15th lecture. And today's lecture is actually part of it will be the last part of chapter 4. Then, as you may know by this time that the midterm will cover everything up to chapter 4. So anything after chapter 4 will not be part of the midterm. So just going over some announcements. Homework 2 is posted, and inshallah let's do this Thursday at 11:59 p.m. And again, use grade score, please. For quiz 3, the date for that quiz is this Wednesday, and the material is 4.5 to 4.11. Omar, question?
ايوه دكتور هل بس لو يعني في إمكانية إن الكويز يكون يوم الأحد، لأنه يكون في مدات الخميس والأربعاء، وفي ممكن ناس عندهم جزء طيارات وشيء زي كذا.
Okay, you have to all agree on that. If you want to start this initiative, just post something on the discussion board and let everyone participate.
Okay.
عدنان؟
دكتور إذا تأجل الكويز راح يزود الماتيريال؟
It's going to be exactly the same material.
يعني ما راح الماتيريال راح يكون نفس.
If you want me to add 2 sections, I can do that for 12.4.13. But okay. Bye. Okay. So just let me go over what we've done last time. So if you remember, we studied something called superposition principle. So we had the situation where we have more than one source, and we were interested in finding the contribution of each more than one independent source, and we were interested in finding the contribution of each independent source. So to apply superposition principle, we said, well, the first thing is we need to deactivate all independent sources except one. Then we need to find the current or the voltage, any value that we are interested in. It has to be like the current or the voltage. We can't use the power for that reason. And then we're going to repeat the same step until we cover all sources. And after that, we will have, say, like we're interested in finding the current passing through a certain resistor. And we have 4 sources. So we have different values of the current. So we're going to add them up. And this is going to be the total. This is going to be the total current due to all 4 sources. You may see this. I mean, it's a good powerful. It's a powerful like computational tool, but it's not. In practice, is not that helpful. Especially if you have if all of them are DC sources, because you can actually directly take the multimeter. A multimeter is a device that measures the current, the voltage, and the resistance and power as well, and directly measure the current that you're interested in. So the multimeter will give you the contribution of all individual sources. But it's a very powerful tool when you do some calculations, because you can see that in some cases superposition simplifies the analysis. Okay.
Sharing the screen.
Yes, I'm sharing the screen. Can you see it, Shabab?
For me, I can.
Yes.
We can see it.
Yes, it's clear, Doctor.
Yes, it's a bit.
Okay, very good. I think, Yasser, you may need to close
Yes,
Teams and so. Okay. In the previous lecture, we stopped with one. We did like one exercise on superposition principle, and this is another exercise for that. By the way, there's just one comment here that I want to mention. The good thing about solving, the good thing about chapter 4 is that any circuit that we actually solved using specific method, you can try to apply a different method. For example, here we can try, say, mesh analysis or node analysis, or any computational technique, or any technique that you want. So yes, we solve it with one technique, but does not mean that you will not be able to solve it with the other techniques. So this will give you extra exercises to work on. Okay, so we have the following circuit. And the following circuit, we have two sources, two independent sources, and two dependent sources. So remember, in order to apply superposition, we have to deactivate only the independent sources, not the dependent sources. The dependent sources have to be active. Okay, so let's start by deactivating the voltage source. I'm sorry, deactivating the current source. So we have a current source, 5 ampere current source, and we want to deactivate it. So if you are to deactivate a current source, what should you do? What should you replace the current source with? Hadi?
An open circuit.
An open circuit. Why, Hadi?
Because in the current, when you have an open circuit, the current equal to 0.
Exactly. So this is why sometimes in some books they don't say deactivate, it says 0 the current source. Okay, so let's actually deactivate the current source, and let's draw the circuit in this case. So if I draw the circuit, it will be something we have 10 volts. I have 5 ohm. I have 20 ohm. I have a dependent current source. This is going to be Vd prime, V delta prime. This is 10 ohm. I have a dependent voltage source, and the value of this is 2I delta prime. So V delta prime is this one. I delta prime is this one. So remember, I'm interested in finding what? V naught. So V naught is the voltage across the 20 ohm resistor. So let's first start by finding V delta here. And who can tell me what V delta is? Okay, V delta will be, remember we have a current source passing through, we have a current, and the current in series, we have this one is in series with the current source. So the current passing through V delta must be equal to the current source. So according to the passive sign convention here, it's going to be minus 10 multiplied by 0.4 V delta 5. Muhammad, Mastri, question? Muhammad, question? You're muted. Okay. طيب.
Doctor,
Yes.
I still can't see the share screen. Maybe I don't want to cut you off, but maybe if you can close the sharing and share the screen again, maybe it will solve my issue.
Can you all see it?
Yes. Now I can see it.
Okay. طيب. Okay, so in this case, if we find V delta, it's going to be minus 4 V delta prime. What do you think about this equation? Yes, sir.
V delta is 0.
Yes, this is only valid if V delta prime is 0. So if V delta prime is 0 means the current source is what? Is an open circuit here. The dependent current source is open circuit. Remember, the dependent sources behave like independent sources, meaning that if they have zero current, if we have a current source if we have a dependent current source that has a zero current, it behaves like an open circuit. If we have a voltage source with a zero voltage, dependent voltage source with a zero voltage, then it behaves like a short circuit. So in this case, no current will be passing through that branch. So no current will be passing for the dependent voltage source and the 10 ohm resistor. So the circuit can be simplified to, because remember we are interested in finding V naught here. So this is 20 ohm, this is 5 ohm. And in this case, we can easily find V naught using voltage divider law. Okay, so this is V naught due to only the voltage source. Now let's study what happens when we activate only the current source. So going back to the circuit, if we activate the current source and deactivate the voltage source, then this one is the voltage source is replaced with a short circuit. So we'll have 5 ohm in parallel with the 20, and everything stays as it is. So let me draw the circuit here. Let us activate the current source. So in this case, I have 5 ohm, I have 20 ohm, I have 0.4 V delta prime, I have 10 ohm, and I have the current source. Okay. So just let me label everything here. So this is I delta prime, or I delta double prime. This is V delta double prime. Again, this is V naught double prime. Okay, so here what I need to do is something, I need to find V naught, remember. I need to find this voltage. That's what I'm interested in. So the multiple ways of doing that. Probably the one of the easiest ways to apply the node voltage method, and in this case, I will set this one as V1, V2, V3, and I set this one as my reference point. So applying the node voltage method will give me starting with node 1. So V1 divided by 5 plus V1 divided by 20 plus or minus 0.4 multiplied by V delta prime. But again, here at this stage, I'm very familiar with node voltage method. So I will see that, well, V delta prime is actually V2 minus V1, minus V3 equals to 0, and this is the first equation. Umar, question?
No.
Okay. Participation?
Yes.
Okay, go ahead and give me the equation for V2.
-5.
Yes. Okay. It's going to be
So
minus
it's going
5.
to be -5,
Okay.
and then plus 0.4 times V2 minus V3,
Exactly.
and V2 minus V3 over 10.
So this is the second equation. The third equation, Ibrahim?
5.
5. Well, remember here, Ibrahim, you have a voltage source connected between a reference node and essential node. So V3 is actually 2I delta.
It's 2I delta.
So what is I delta prime here? Or I delta double prime?
It is V1 over 5.
It's actually, no, it's negative V1 over 5.
Yes.
So it's going to be negative V1 over 5. So minus 2V1 divided by 5. So this is the third equation. So I have 3 equations, 3 unknowns. So if I solve for them, I will get V1 equals to 16 volts, which is again, V1 is actually V0 double prime. So the total V0 will be 24 volts. Okay. Any question, Ahmed?
دكتور، المعادلات السيركت اللي يكون فيها independent sources مو لازم اني اجيب معادلاتهم؟
Yes.
ولا عادي؟
Yes, that's what we did. But remember here, we're not interested actually, we're not trying to explain node analysis here. So this is the equation, this is V delta. So what you need to do here is to write V delta double prime. Then here I delta double prime. Then you will realize that you have 4 equations. You have 3 equations and 4 unknowns. The issue is that you cannot do it with your calculator. So you need to actually substitute.
Analyze.
Yeah. So until you reduce it to 3 equations and 3 unknowns.
Okay. Thanks.
But if you're not sure, we can do it like this and do the substitution. And just want to throw it very quickly because I'm assuming everyone is strongly familiar with node voltage method. طيب.
Yes. Thanks.
طيب. Well, that's it for chapter 4. And chapter 4 is one of the fundamental chapters in this course, because if you remember, we learned very useful circuit analysis techniques that are going to be useful in the remaining parts of the course. But if you recall, the only we had 3 components. Basically, we had 3 components. We have resistor, we have voltage source, and current source. Well, resistor is a passive circuit element. Okay, a resistor is a passive circuit element. Sources are not. So we have 2 more passive circuit elements that we need to introduce, and then we will go to complicate the analysis to include alternating current. So we may need to stop here for a while and study the difference between DC and AC current. Allah la yasallutam. Okay. Between DC and AC currents. So the voltage and the current we studied here, they are kind of constant with respect to time. So if you have a battery, if the voltage across and you connect it to the circuit, then the voltage produced by this battery or generated by this battery will be constant all over the time until the battery is dead. This is very useful because if you look into any electronics, any electronic component in your cell phone or desktop or laptop or any electronic component, they usually work with DC. And they use this DC voltage to kind of like either perform some logic operation. For example, if you have if you want to apply, if you want to, for example, transmit 0101 in a PC or something like this, then you will have there's no one actually. You will have like one is directly, the state of one is directly connected to the voltage source, and the state of 0 is connected to the ground. So in both cases, you have two voltage level. One is a constant DC source, and the other one is 0. And this is very useful. We're going to use it all over time in applications and even like in analysis. But if you are to transmit power from one place to another, then using a constant voltage source is not something that you prefer. The reason for that is there will be a lot of losses associated with a constant or DC source. So what you need to do is you need to create some sort of power or some sort of voltage or current that alternating with respect to time. So in this case, let's see. So in this scenario, you have a constant. So if this is your time axis, this is the voltage. And if you plot it, it will be something like this. And this is what we had so far. What we will see, inshallah, is in chapter 9, is something like this. This is time. It will be something like this. This is voltage. But we need the analysis in chapter 6, 7, and 8 to serve as a transition between moving this way, between a circuit with this type of sources to circuit with this type of sources. So what we're going to do here is in chapter 6, 7, and 8, we're going to kind of like create some sort of like smooth transition from purely constant sources to studying, okay, what happens if we just turn on the switch, if you just turn on the voltage source, if you just connect the voltage source. So there's some sort of intermediate response that's gonna last for very, very few seconds, very few milliseconds actually, or even less, that we need to study. Then we will study what happens if we have something that's alternating, something that's actually, it's not constant at all time. And that's what we're going to do in chapter 9. And going back to why we're using alternating current is that if you want to transmit energy over, if you want to transmit power over long distances, then you need to, if you recall, power is I multiplied by V. So for a constant power, you can have constant I and constant V, or you can increase V, decrease I, or the opposite, increase I, decrease V. So if you increase the current, it means the power dissipated in the cables are increased, because the power dissipated in the cable is I squared multiplied by the resistance of the cable. So what they do is, yes, we transmit the same power. The power is exactly the same, but we increase the voltage and decrease the current. And at the receiving end, we bring it back to the normal situation, or to the current level that we are interested in. Again, this is maybe something that we can cover in AE 230. So any question about DC circuits, AC circuits?
دكتور هذا is it the beginning of chapter 6?
Yes.
Okay.
It's not in the beginning. I just introduced it, so it's not. If you look into, I think if you look into your book, it's not there.
Thanks.
The cream.
Doctor, is there a power or an energy lost between converting AC to DC?
Well, what you do, you're not converting DC to AC. So you're generating the power generated is actually AC. Then at the receiver usually is you're converting AC to DC. So usually there is no power loss, but I'm not saying ideally no power loss, but any component has some power losses associated with it. But it's very small. It's not that big deal. So one of the interesting applications here, it's something that I've been doing, is something called energy harvesting circuits. I don't know if you've heard of it. I don't know if you've seen RFID tags or something like this. So you have an antenna, and there is no power source associated with. You have a device, a tag called RFID tag, and that device doesn't have a battery, and it still operates. How does it operate? So you are shooting. You have another device that's shooting AC power at very high frequencies. Then you take this AC power and then you rectify it. Rectifying meaning AC to DC. Then you use it to power some sensors. Then you use your feedback here. You connect your antenna here to different resistors, R1 and R2. Or as we can see, they're different impedance. Then you start switching between those. So if you switch between this one, you will get specific type of reflection. If you switch to this one, you'll get specific type of reflection. So what you do is like, it's a lot like, so you're using this power, you're receiving power. So part of it will be used to actually create a power to your circuit. And this part was going to power up some sensor, for example, temperature sensor, heart monitoring, any type of sensor. Then in order to communicate the data to your receiver, what you're going to do is something much easier. What you're going to do is something varying some of the resistors here. So you're changing the reflection. You're changing the reflection of the wave that's actually hitting your antenna. So this one is called energy harvesting tags. because they harvest integrated. You don't have it. عدنان.
دكتور معلش، لكن اللي بناخذه هل هو مثل لما نحول analog signal to digital signal؟ هل هو it's the same case يعني؟
Not really. When you convert it, you're doing some sort of comparator and other circuit methods.
Okay.
So it's not free. So in order to analyze, in order to do all these cool applications, we need to introduce two more important components, two more important passive components. The first one is called inductor. The second one is called capacitor. You probably have seen them in physics 1 or 2, but we're going to discuss them in a detailed manner. Okay, so what is the inductor? An inductor is an electric component. It's a passive component that opposes the change in the electric current. So if there is a change in the electric current, then the inductor will be some sort of, will kind of like oppose the abrupt change in that current. Also, inductor is actually a circuit element that stores magnetic energy. Remember, we have electric and magnetic energy. So inductor is a circuit element that's going to, or that stores the magnetic energy. On the other hand, capacitor is a circuit element that stores electric energy. Okay, that's enough about the theory of them. If you're going to take EE 340 or Physics 305, then you will study them in a detailed manner. Okay. Now, how to use them in circuit? Well, first of all, we need to assign symbol for them. So remember, we have R for resistor. So the symbol for an inductor is L. The unit of the inductor is Henry. And remember, so we assign symbol for them. Then we need to study the relation between the voltage and the current in the inductor. So if you recall, for a resistor, we have something called Ohm's law. We have Ohm's law. For Ohm's law, V equals to R multiplied by I. For inductor, the current and the voltage are related by this equation. V equals to the inductance multiplied by the derivative of the current with respect to time. What does it tell you this? di by dt. Actually, it tells you it tells you a very important thing, that if you have a constant current, then the voltage is zero. Okay. What? Well, at what case, or what is the case, or when this case hold? Well, Muhannad?
In a short circuit?
Well, not really. Abdulkarim?
I had the same answer as him.
Okay. Abdullah?
Open circuit?
Not really. Okay, طيب. If you go back to the first thing that we discussed when we started chapter 6, we said like we have DC and AC current. For a DC current, for a DC power, the current is constant. So the voltage is going to be across, if we have a DC source, if you connect an inductor to a battery, an ideal inductor to a battery, and then you try to measure the voltage across it after a very long time, not immediately after connected, you will see that the voltage will be zero. And this means that the inductor at DC behaves like a short circuit. Okay. It tells you Okay, this is exactly what it tells you. Right. Again, here we are following the passive sign convention, so we're assuming that the current is entering from the positive terminal of the inductor and leaving from the negative terminal of the inductor. So the first thing we realize here that the voltage and the current are related by the following equation. So V equals to L, the derivative of current with respect to time. So if we have a current that's constant over time, then the voltage will be 0. Ziad?
The di over dt, can we approximate that to be like the acceleration for the charge?
Well, the charge, the rate of change of the charge, yeah, you can do that. Yes, in order to have a response like this, you have to have a charge that's not moving with constant velocity. So the charge should move with the charge should have some acceleration. Okay, let's study more properties of the inductor. If the inductor is, again, this is exactly what we said. If the inductor is ideal, what we mean by ideal? Usually we have an inductor. This is the ideal inductor. The non-ideal inductor is something like this. And this one can be modeled as a single device, we call it non-ideal. So a non-ideal inductor has a series resistance associated with it. And in this case, if we have constant current, then the voltage will not be 0 because you still have a voltage drop, because this is the part that's going to behave like a short circuit, but this one is actually small resistance, so you'll have some voltage drop. But again, if the current is ideal, then the voltage across it will be 0. And remember here, since we have di by dt, this tells us that, well, the current cannot change instantaneously across an inductor. So if the current changes instantaneously across the inductor, it means the derivative is not defined. The voltage is not defined. So that's why, if you recall, an inductor is a circuit element that opposes the change in the current. So you cannot just like connect the battery and then the current is 10 ampere, and right before you connect the battery, the current will be 0. So you cannot have this abrupt change. Okay, so now those are some pictures of inductors. This is the one that's used in a printed circuit board, and those are some inductors that you can find in the lab or any circuit. Okay, let's have an exercise. Let's do one exercise here. So what we have is the following. So we have independent current source, and this current source is connected to an inductor. So it generates 0 current for t less than 0, and a pulse 10t e to the power negative 5t for t greater than 0. Okay, you can see here that you're not changing the current instantaneously across the inductor, because the initial value here is 0, then it will start increasing. So the very first part is asking you to sketch the current waveform. I'm not going to sketch it, so I have it somewhere in here, and this is it. So you can see that current is 0, then it will start increasing until it hits its peak, then it will start decreasing. Okay, this is the first part, very simple. The second part is asking us at what instant of time is the current is maximum. Al Yusuf?
We take the derivative of the current and then set it to 0.
Exactly. So we have the expression for the current, and we take its derivative and set it to 0. So the maximum is di by dt equals to 0. And in this case, di is 10t e to the power negative 5t. So if we take the derivative, it will be so if we set it to 0, then we get 1 minus, I believe there is a t here.
There is a 10.
1 minus 5t equals to 0, so that one is cannot be 0. So this implies that 1 minus 5t equals to 0, and t equals to 1 over 5, or 0.2 seconds. So as you can see here, at t equals to 0.2 seconds, we have the maximum value. Okay. Now the the second or the third part is asking you to find the voltage given the inductance as a function of time. So let's see. I need a new name. Ibrahim. Ibrahim. Umar.
Yes. V is equal to L times the derivative of I. So we have the derivative of I. It's so just multiply it.
Right, L, which is 100 milli or 0.1.
Yeah, exactly. Times 10
Yeah.
e to the minus 5t.
So if I simplify it, I will get something like this. RT greater than or equals to 0 and 0 for t less than 0. Okay. So the fourth part in asking us to sketch the voltage waveform. Again, I'm not going to sketch it. I'm going to use the fact that it's somewhere in the slides. Okay, we're done with. Okay. So the fifth point is asking us, well, are the voltage and the current at the maximum at the same time? And clearly from the way we sketch them, they are not, because the voltage is maximum at t equals to 0. The current is actually maximum at t equals to 0.2 seconds. So the answer is simply no. Current max t equals to 0.2 seconds. Voltage max at t equals to 0. The sixth part is asking us what instant of time does the voltage change polarity? اوكي طيب علي طارق.
It is 0.2 because it's change from positive to negative.
Okay, exactly. So at t equals to 0.2 seconds. Okay. The seventh part is there any instantaneous change in the voltage across the inductor? What do you all think? طيب حسن الصايغ.
أجرب جراف. I don't think so, Doctor. There is no.
Okay. Who else thinks otherwise? طيب وليد وعقيل.
Yes, there is.
When is it?
T equal to 0.
Yes, t equals to 0. So you see here, there's a jump. Okay, Amr, question?
Yes, doctor. I didn't get the last question.
So the last part is asking us, is there any instantaneous change in the voltage across the inductor? Because remember, we said that the current across the inductor cannot change instantaneously. What happens to the voltage? And we saw here that the voltage is actually, there is at t equals to 0, the voltage change instantaneously.
Yeah, okay, thank you.
Okay. So now if you recall, what we did was we derived the voltage. We found the voltage using the current. So now what happens if you're giving the voltage and you're asked to find the current? Then let's write an expression for that. It's simply the integral of V multiplied of L di by dt. So if you recall, so remember, if we're given the current, then we can take its derivative and multiply it by the inductance, and this is going to give us the voltage. Now, what if we are giving the voltage? Can we find the current? And this is exactly what we're trying to find. So if I multiply dt, if I multiply both sides by dt, I will get v dt L di. Then I need to integrate both sides. So from t naught to t v, I need to change the integral variable. Okay. And here it's going to be so if I integrate both sides, I will get so now I of t is going to be 1 over L multiplied by the integral of between t naught from t naught to t cos so this is exactly what I'm looking for. So quick question. will this expression give you, or would this integral give you a value or a function? This can.
It should be a value.
I guess.
No, it's going to give you a function. It's a lot like you're integrating from 0 to x dy. So this is going to give you x, which is not a value here in the function. And remember, we're interested in finding the expression. Much like this one, this is not going to give you the value, this is going to give you the function, and you need to evaluate it at a specific point in time. Okay, let's see how can we how we can apply this in specific exercises. So in this case, remember the previous one, we had a current source connected to an inductor. In this case, we have a voltage source connected to the inductor, and it's the same inductor. The inductance is 100 millihenry. And for t less than 0, the voltage is 0. Then at t equals 0, we connected the voltage source. The voltage source has the following flow. So it will start increasing, then it will decay. And the first thing I asked about is actually to sketch the voltage as a function of time. So again, I'm not going to sketch it, so I have it somewhere. So this is what happens if we plot the voltage as a function of time. Okay. Now we are asked to find the current given the voltage. Salman?
Yes, we apply the formula. The current equals to 1 over L multiplied by the integral from t naught to t of the voltage plus I.
Okay, 1 over L. So what is T naught in this case?
T equal to 0.
Exactly, because this is the initial time instant.
Yes.
Okay, V tau. So the current here, since it's there is no voltage applied, nothing is there, so no current applied through the inductor, so the current is also 0. So now we need to simply apply 1 over 1. We have 20 tau e minus 10 tau d tau, or 2000 200 so if I so if I integrate this one, I need to integrate it by part or using the table. So what I'm going to do, I'm going to use the table here. Then if I differentiate this one, I will get 1 minus 1 over 10, 0, 1 over 100, e minus 10. So I is going to be minus tau divided by 10, a minus 10 tau, 1 over 100, or if I simplify it, it's going to be something like this. Okay, So now I need to substitute. So I have 200 multiplied by so I will end up with the following expression for the current. So it's going to be 2, 1 minus t, 10t, a minus 10t, a minus 10t, and this is true for t greater than 0. Question? Yes, sir? Rahim? Okay. So now we found the expression for the current. The third part is asking us to actually sketch the current as a function of time. So again, I'm not going to do that. I know it's there. So what you should do in this case, you can take the expression for the current and just plot it. And this is going to give you the plot of the current versus time. So as you can see here, the final value of the current is not 0. The reason for that is when the voltage source is off, when the pulse dies here, you will have a short circuit, so you'll have an wait, sorry about that. Okay, can you hear me, Shabab?
Yes, doctor.
Yes.
Yes, yes.
Yes, we can.
Okay. So again, since we okay, can you see my shared screen?
Yes, doctor.
Okay. Why cannot? Can you?
Yes,
we
we
can.
can.
Okay.
Yeah, we can see.
Okay, because I cannot see it here. Anyhow, okay. No problem. طيب. Okay. So since we have an ideal inductor, there will be no power dissipated in the inductor itself. So in this case, the final value of the current can be found by taking the limit as t approach infinity of it and this is going to give us 2 amperes. Okay, طيب. Any question? Go back and check in. طيب. Okay. Good. So we calculated, or we derived the expression for the current, the voltage. Now let's move on to something else important, which is the power and energy. So if you recall, that P equals to IV. So this is always the definition. And we know from the inductor that V equals to di by dt. This is for inductors. And if we're trying to substitute, P equals to IV, V equals to LDI by dt, so it's going to be L I di by dt. So this is the definition of the power. Also, we know that power is always the derivative of energy with respect to time. So this should be equal to di by dt. So now what we want to do, we want to relate energy to current. So if we factor out dt, so we're going to get dw Li di. Then we need to integrate it in order to express the energy in terms of the current. Li I of t naught I of t di. Okay, we can assume that the initial value of the current is 0. So this implies that the initial energy is 0. Then the energy is Li squared. So we have a shortcut, or if we have like a quick formula for calculating the energy, provided that we have an inductor. So if we have an inductor, then the energy will be half of the inductance multiplied by the current square. Okay, so let's summarize what we did. So we have voltage. We calculated the voltage, or we know that the relation between the voltage and the current. We know the yes, Shabab, Ibrahim.
Doctor, I didn't get from where we got the half in the energy equation.
Okay, we'll come back to it. Umar.
So, Doctor, does that mean that the energy is constant?
No. Okay, hold on a second. Okay, we'll come back to the question. So let me go ahead and continue. Like, so I is if we are given the voltage and we want to calculate the current, then we can use this formula. The power is simply I multiplied by V, or there is a shortcut for that, Li di by dt. This is special for the inductor, and energy is half of the inductance multiplied by I squared. So those are the 4 important formulas associated with the inductor. So maybe this is the most important formula. Then everything else you can derive from there. So let me go back to. I'm sorry. This one should be part of the integral. Is it clear from where we got half, Ibrahim, now? Ibrahim? So if you have x dx and you want to integrate it, will be x squared divided by 2. And this is what happens.
Yes, I got it.
Omar, your question is what? Right.
That if the power is going to be constant or not.
No, not really.
Sorry, not the power. I mean the energy.
No, not really. The current can be a function of time.
Yeah. Okay.
And the energy will be a function of time. As we're going to see this in a moment. So we're going to solve an exercise in which we have a current and a voltage, in which we have all of these forms are, all of these quantities are a function of time. So basically, if we go back to exercise 2, this is exercise 2. We have a current source and parallel with the inductor. And we asked to plot the current, the voltage. That's what we did in that exercise. Now we'll add the power and energy versus time. As you can see here, this is part 1. And those are the plots. You can see here, Umar, that they are not constant with respect to time. So this plotted using I V. So you take the product of these two curves, and this one is 1/2 Li squared. So you take the first plot, square it, and scale it, and this can give you the energy. Okay, واضحة؟ طيب. Now we have these plots lined up. So we want to study them deep. So in part 2, or question 2, is asking us at what time interval the energy being stored in the inductor. So remember, inductor is a circuit element that stores magnetic energy. So at what point in time that the energy is being stored in the inductor? Yasser?
From 0 to 0.2, because we have an increasing curve. The energy is being stored.
Exactly. So, or you can look at it this way: when the power is positive, so meaning that if we have something with positive power, it means that it's using the energy or it's absorbing the energy, صح? If we have a negative power, it means that the circuit element is actually releasing energy. So when the power is positive, the inductor is absorbing energy or storing energy, and when it's negative, the inductor is actually releasing energy or delivering energy. So energy is stored when the energy increases with respect to time. And this is exactly the same interval. Or when the power is greater than 0. Okay. At what time interval the energy being extracted from the inductor? Remember, the inductor is a circuit element that stores energy. So, okay. So at what point in time? Just hold a second. Abdul Karim.
When the power is negative.
Okay.
So from 0.2 till 1.
It's actually when the power is negative. So from 0.2 to infinity. Because the value is very small, so that's why you can see that you can assume it is 0. Okay. So what is the maximum energy stored in the inductor? This is a very interesting exercise. And this is a very interesting part. So when the energy is maximum, is actually when the current is maximum. Because remember, the current is, the energy is 1/2 inductance multiplied by the current. So energy is maximum when the current is maximum. Remember, this is the same exercise that we solved. So from exercise 2, this occurs when t equals to 0.2 seconds. Okay, so what is the current at t equals to 0.2 seconds? So this is going to be 0.736 amperes. So maximum energy is 27.7 millijoule. Okay. Now we are asked to evaluate two integrals actually. B dt by dt from 0 to 0.2 and from 0.2 to infinity. So let's start with the first one. First of all, we need to find the expression for the power with respect to time. Again, power is V multiplied by I. So in this case, we have 10t E minus 10t minus 50 t squared A minus 10t. And the unit is watts. So if we integrate from 0 to 0.2, then we will get 27.7 millijoule. So you can do it using an integral by parts. If you integrate from 0.2 to infinity, you should get so what happens is this is power generated or power stored. This is power extracted. So if you sum them up, you'll get 0. So the inductor will charge until 0.2, then it will start discharging until t equals to infinity. So the total we have the energy stored equals to the energy extracted. Okay. Now we want to do that for exercise 3. And remember, exercise 3 is exactly the same as exercise 2. The only difference here is we have a voltage source. And if we plot for exercise 3, if we plot the voltage, this is the voltage, the current, the power, and the energy. So this is which part? So we repeated part 1. Part 2 is asking us to what time interval the energy being stored in the inductor. So we can go back and see the expression for the power, and we see that the power is always positive, or the energy is always increasing until it saturates. So this means that it's always stored. And this actually eliminates the fact that we don't have any energy extracted from the inductor. And then the last part is asking us to the following. In exercise 2, or actually exercise 3, why is there a sustained current in the inductor as the voltage approaches 0? And this is exactly what we mentioned here. So since we use ideal inductor, the current will be circulating forever after removing the voltage source. So you remove the voltage source. So the voltage source now, when it's deactivated, it means it behaves like a short circuit. So the current is there in the inductor, and the inductor is ID. So there is no point inside the circuit for the inductor to be for the inductor's energy to be dissipated. So we have used, or we have ID inductor. So the current will be circulating Okay, that's it for today. Oh, sorry, I went 2 minutes over time, so we'll see inshallah next class tomorrow. عمر؟
ايوه دكتور، بس دكتور ممكن لو سمحت تسمح لي اكتب في الروم حق الدسكشن، لانه كتب لي restricted.
طيب. Okay, I will fix it. Yasser?
Doctor, can you explain the last part again? I did not really get it.
Okay. So let's go back to exercise 3. Right. So Vt equals to 20t e minus 10t. And after a while, this value will be almost 0, صح?
Yes.
Okay. So we're not removing the voltage source. The voltage source is there, but its value is 0, so it behaves like a short circuit. So the voltage source generated the current in the inductor.
Yes.
Okay. So if you have a current in the inductor and there's no point for the current for the energy to be dissipated, what happens to you have an ideal inductor? So an ideal inductor is behaving like a short circuit. So it's a lot like all of a sudden you're putting a current inside a loop, and energy will not be dissipated. So what happens to the current?
It will go forever.
Yeah, it will circulate forever.
Yeah.
That's exactly what happens.
I got it. Thank you.
Okay. Questions? Okay. Omar, let me just fix it. And maybe you need to check like in half an hour or something like this. We'll see you inshallah tomorrow.